So I made a picture. Um, it's on neuroanatomical circuitry. Um, Super cool, super cool. So where do I start? Do not take this for fact. This is a good introduction, but like it's not. It's all from memory. So I wouldn't take this onto your exam tomorrow. You'd probably get a passing grade, but whatever. If there's even such a thing as school anymore. Yeah. So, what's next? So, the point of this lecture is to go over the differences between VI and human brains, organismal brains, carbon based brains, whatever. So, the differences and similarities between them. So, one of the differences in virtual intelligence formation and this kind of formation, that was the wrong term, between a virtual intelligence development and the maturation of a neuronal structure. The difference is that neuronal structure is layered by age, evolutionary age of the structures, of the areas of the brain. So the brainstem is the oldest. Cerebellum's a little older. The cortex, the outside, is pretty new. That's basically what's going on. And in a VI, things are structured by relevance to their artifacts. Which leads me into the next point I wanted to make, that each lobe here, this system right here, they all have their own artifacts that they are connected to, right? They all have their own artifacts that they're connected to, that they get input from, and it lets some things change, sends signals in new, novel ways, changes the pattern. So my question, of course, is how do these artifacts alter the development of the brain? Who knows? Because no one has ever told me that neurons have certain rules of interaction that allow a brain to form. They have told me that the genetic code has the code to make everything. That's not particularly the point, though, of a genetic code. What is in my pocket? Great. So, no one's ever told me the rules. All they've ever said was the genetic code encodes for proteins, and these proteins move the cell, efficiently place the cell. But as we know, things have rules of interactions. They will just be more abstract for a genetically designed particle neuron thing. This is because there's code in proteins, and we have to know the rules of interactions by what the proteins do on a cell, what the cell does as a whole. So it's a little more complicated for neuronal development than a virtual particle to develop into organ. Yeah, so let's move on from whatever I was talking about and go right into the picture. So every lobe has its own artifact, right? The limbic system has the olfactory artifact. The occipital lobe has the eye artifact. The temporal lobe has the ear artifact. And the cerebellum has the hand artifact. The signals are sent back and forth either through the brainstem or directly into the lobe and out through the eye. I mean, it's very possible that the cerebellum has connections right into the eye. Very possible. For movement and coordination of the eyes. Okay. So, here's a circuit. The nose sends its input into the limbic system, which sends it to the parietal lobe. Temporal lobe's ear sends its info to the parietal lobe. Occipital lobe, parietal lobe. Cerebellum to the parietal lobe. So, and then the parietal lobe probably sends information to the frontal lobe, and frontal lobe's trying to influence the parietal lobe. So they're all trying to influence each other, right? Or trying to get their information integrated. Oh my god. I got shit in my eye. Okay. So, yeah. That is a neuroanatomical circuit. There are structures. They connect to other structures and they send signals through their connections to other structures, all the while influencing each other. So that's like on a very large scale. On a smaller scale is the limbic system itself. So each of these green things, these green, things, circles, bulbs, they're all formations of neurons. They're all formations of about 10,000 neurons. I made that number up, but let's just imagine the size of our finger, which is probably 50,000 cells. Who know? I do not know. I do not know how big I am. So, yeah, each of these green things are formations, and these formations of structure are all networked together in two ways. The formation itself is a network of neurons. The formations are networked together with other formations in the limbic system to exert influence on each other. Some are exerting influence over the hippocampus for memory, and the hippocampus is exerting influence over the amygdala for emotions, and the orbital frontal cortex is bringing the frontal lobe's influence into the limbic system. So let me explain all that for a sec. So the limbic system is why animals have emotions, right? We can control our emotions, and some animals can control their emotions better than other animals because they have a bigger orbitofrontal cortex in the frontal lobe. So the more highly developed the frontal lobe is, the more influence the frontal lobe has on the limbic system, which is deeper in the brain. Very slightly deeper, but... And by slightly, I mean probably millennia back. A long time. A very long time. The limbic system hasn't been around. And the orbital frontal cortex has probably been around for about 3 million years, and the limbic system has probably been around for 20 million years, 65 million years, who knows? I do not. But the point is, they are all networked together. These formations of networked neurons are all networked together to exert influence on other areas of the brain. Alright, so I guess I kind of did this backwards. I guess I went from the top to the middle. Now I'm going down a little bit more. So now I'm going to talk about a specific formation in the limbic system. It's called the hippocampus. It's for memory formation. So I'm going to talk about how it works in the network, how it works in memory, and not the other thing because I already went over it. So, down to my last cigarette. Name. If I didn't chain smoke them. Anyway, so the hippocampus works in network by having inputs from other formations send inputs into it. Now, this is the point where in my last video I had to explain how a neuron works compared to a particle. Love this song. Oh, look, I left it up from the last video. Alright, so here's a neuron, right? Its signaling threshold is reached, and it sends an electrical signal down to the accumulation of the neuron. Then neurotransmitters are released, and they bind to the next neuron, and the next neuron opens its gates, and potassium flows in, or sodium, or whatever. I don't remember. But electrically charged chemicals or elements go into the neuron and activate its electrical potential signaling threshold, which sends a signal to the very end of the neuron, down its axon, and at the very end, neurotransmitters, they're just chemicals that bind to other neurons, get sent out, bind to another neuron, open that neuron's gates, or close that neuron's gates. It depends. It doesn't matter. Lots of variation and diversity. The signal gets proliferated or it does not. So what does that have to do with the hippocampus? That's just how neurons work. How does the hippocampus work? So these structural changes that the neurotransmitters do to these cells, that is how memories are formed. So let's say you're forming a memory, and you get a shot of adrenaline, right? It's going to change the way things bind, and the adrenaline's going to bind to the hippocampus. It's going to bind all over the place, but it's going to alter the way the memory is encoded in the structure of the hippocampal formation. Okay. And it's just gonna, once it has the structural change in it, it's going to exert influence on its other things. It's not like the memory itself is encoded. It's just a structure. And that's why memories are imperfect, because it's just the way the brain decided to encode it. And it's not the way the brain decided to encode it, it's the way that the system reacted to the information. Memories are not reality. Pictures are more reality than memory. But memories feel good, so do pictures. But that's all beside the point. I think I'm done. So this was a neuroanatomical breeze through. Cool. Thank you for checking out my picture and watching. It was nice talking to y'all. See ya.